Welcome to this class on curve sketching. As you may remember from your high school days, in curve sketching, what we're trying to do is change the formula for a function into a nice looking graph. In fact, we're trying to change it into an accurate looking graph, whether it is nice looking or not. So for those of you who are artistically minded, this could be a fairly interesting and rewarding activity. For some of you who are not, well, it's still quite challenging because there is a lot of variety in it, and there is a lot of aspects to it, and it really is something that ends up never repeating itself or does not become boring. So in this class, in this lecture, I'm simply going to remind you of how to get the whole activity organized, and then of course in class we'll do some examples together, and then I will let you loose on a number of other examples. So the main idea here that I want to bring out is the fact that when you're sketching the graph of a function, you want to change the formula of a function, something written as y equals f of x, into a graph. And we're going to do that by using three main tools, all of which are by now familiar to you. The first one, of course, is the function itself. We're going to be using the function and some of the calculus methods that we have developed around the function to get some basic information about the function, basic graphic information about the function. Then we're going to use the first derivative to get some more information, and then again the second derivative to get some more information. Now, I would like to draw your attention to the fact that in my experience, many students coming from high school tend to focus primarily on using the derivative in order to sketch the graph of a function. But if that's all you're going to use, you're going to have very little to go on, and quite commonly you're not going to have enough information to sketch an accurate graph. So I'm going to give you an outline of the piece of information that you need from each of these three tools, and I strongly encourage you to make sure that you use all three whenever you're sketching the graph of a function. So let's start by seeing how we can use the function itself, the original function. What kind of information can we get from the original function? Well, we can get information on the domain, things like points of discontinuity, things like, for instance, single point holes, or possibly jumps, or any of the other discontinuities that we have seen before. And of course, we're going to be using limits to analyze and identify those, as well as vertical asymptotes. Those also come out from the function itself by using limits. We can also use the original function to find the intercepts, be it y-intercepts along the y-axis or x-intercepts along the x-axis. And finally, we're going to be able, by computing limits at infinity, positive or negative, we're going to be able to find out if the function has asymptotes, horizontal asymptotes. So these are the main pieces of information. Altogether, if you think about it, these pieces of information are going to tell us where the function is. Where does it hit the axis? Where does it have holes? Where does it have asymptotes? How does it exit the field of view, and so on. So it's all about where are the main features of the function. Once we've done this, then we're going to move on to the first derivative. And we're going to use the first derivative to get information on, as you might imagine, patterns of increase and decrease. So we're going to find out where the function goes up and where the function goes down. And of course, based on that, by using a first derivative analysis, we're going to be able to identify its extreme points, both the max and the means, and of course, those being the relative ones. Some of them may be absolute ones, but the first derivative analysis will only be able to identify them as local or relative extreme points. So altogether, the question that the first derivative answers is, which way does the function go? Does it go up or does it go down? And so again, we're going to use the first derivative to find that kind of information. And finally, we're going to use the second derivative to get information of, yes, you guessed it, the concavity. We're going to find out if the function is concave up or concave down, and of course, in relation to that, whether it has inflection points and where those inflection points are. So in other words, the second derivative tells us, gives us the answer to the question, how does the function curve? In a way, the second derivative analysis really is an icing on the cake, in the sense that we can get most of the information about the function without looking at its second derivative. The second derivative can be used to put the final touches, as well as to confirm maybe the information that we have obtained thus far. Being human, it's possible we're going to make mistakes in analyzing the function and its first derivative, and if we analyze the second derivative as well, maybe some of those errors will be showing up. And so we use that again to provide additional details, additional piece of information, as well as to make sure that everything fits together. So this is basically what we're going to do to sketch the graph of a function. Now, a couple of more pieces of advice about that though. As you put all that into practice, so if you try to execute this graph sketching procedure, you may want to think about a few points. First of all, make sure that as soon as you find one piece of information, you mark it on the graph. Don't wait until the end to put it all together. It will not come all together. What you want to do is you build it piece by piece, just like you build a house piece by piece. You're not going to just sort of scan the house left to right and build it all. You'll have to do put in a frame, and then all the electrical part and all the plumbing and so on and so on. So that's the same thing that you want to do with graphing a function. So let's say you find intercepts, mark them down. You find asymptotes, mark them down. If you find max and mins, mark them down, and so on and so on. Then, after you have all these pieces identified, try to connect them all together in a way that is consistent. Okay, so make sure that you don't have to force or twist your curve in order to make it fit all the features that you have found. If you realize that there are some features that need to be forced into the graph of the function, probably there's a mistake. And so at the end, what you want to do is you want to also check that you have avoided any contradictions. Okay, so make sure that if you found out that the function is supposed to be increasing on a certain interval, make sure it is increasing, and make sure that that interval of increase also is consistent with the intercepts, with the concavities, and so on and so on. So try to do all these things again one piece at a time. You are very much building the sketch of the graph, and you're not trying to come out with it all together as sort of a big major vision coming from the sky, but that you're going to be able to build it up one by one, checking what you're doing and making sure that the end result doesn't look silly. I trust you're going to do that, and so we're going to see in class how that gets done on a few examples, and then more examples on your own practice.